This lecture will cover the relationship between mass and volume. Additionally, the concept of flow rate is introduced. Density is an intensive material property, equal to the ratio of mass to volume for a sample of the material. Being an intensive property, it is independent of the mass of material. Density is calculated by measuring volume and mass for a given sample. The inverse of density is referred to as the specific volume and is equal to the ratio of volume to mass. Common units for density are kilograms per cubic meter and pounds mass per cubic foot. You may think of density as a conversion factor for mass and volume. Unlike conversion factors for units of dimensions, this conversion factor is material dependent. Density is material dependent, but also depends on temperature and pressure. The density of a liquid or solid is slightly dependent on temperature and pressure. The temperature dependence typically is greater. Gas density is strongly dependent on pressure and temperature. The dependence is given approximately by the ideal gas law as density is equal to the pressure divided by the ideal gas constant R divided by temperature. Values for density commonly are reported in reference books or the literature as specific gravities. Specific gravity is equal to the material density divided by a reference density. It may be considered a relative density. Specific gravity is abbreviated as SG. The value for the reference density must be provided along with the specific gravity to calculate density from specific gravity. Commonly, the density of water at 4 centigrade is used as the reference density. At 4 degrees C, water has a density of 1,000 kilograms per cubic meter or 62.4 pounds mass per cubic foot. The notation, SG, and in parentheses, 20 degrees over 4 degrees, is used to indicate the reported specific gravity is for a material density measured at 20 degrees C, and a reference density of water at 4 degrees C. To calculate the specific gravity for a material at 20 degrees C using water as a reference at 4 degrees C, the density at 20 degrees C in units of kilograms per cubic meter is divided by 1,000 kilograms per cubic meter. Note that specific gravity is dimensionless. In Lecture 1, we introduced the general process flow diagram above to illustrate a generic process for converting raw materials into higher value products. Most processes will consist of a reaction section in which a chemical or physical transformation converts some of the raw material into the desired products, and a separation section in which the desired products are purified. For continuous processes, the sections are connected by pipes, and material flows within each section and between them through pipes. To design such processes, we must understand the terminology for specifying flow rates in pipes. This image illustrates a portion of the pipe network in a chemical plant. You may hear chemical engineers be referred to as plumbers because of the prominence of pipes in a plant. Flow rate is the rate at which material moves. A rate is defined to be an amount divided by a time. Two types of flow rates are used in engineering calculations: mass and volume. Mass flow rate is the amount of mass that flows divided by the time interval over which the flow occurred. Similarly, volumetric flow rate is the ratio of volume that flows to the time interval over which the flow occurred. Density is used to convert a mass to volume flow rate and vice versa. Note that a dot over the letter M or V is used to differentiate flow from amount, and we will refer to mass flow rate as M dot and volume flow rate as V dot. To measure flow rate, the flowing material is collected for a specified amount of time. For example, to determine the flow rate in a pipeline transporting crude oil, one could collect the oil from the end of the pipeline for an arbitrary period of time. If 25.6 kilograms is collected in 1 minute, the flow rate is 25.6 kilograms divided by 1 minute, or 25.6 kilograms per minute. If volume is measured instead of mass, the volumetric flow rate can be calculated from volume divided by time. If both measurements are made, mass and volumetric flow rate can be calculated. Dividing the calculated mass flow rate by the volumetric flow rate, the collection time used for the measurement cancels to yield the ratio of mass to volume, the material density. Thus, mass flow rate is equal to volumetric flow rate multiplied by density, just as mass is equal to volume multiplied by density. This table summarizes the different ways the relationship between the mass and volume of an amount can be written to convert mass to volume or vice versa. The relationships between mass and volumetric flow rates are identical and given by substituting the flow rate for the amount. Instead of volumetric flow rate, bulk velocity, V sub B, may be used to specify flow rate. The cross-sectional area of the pipe also must be provided to calculate flow rate. Longitudinal, along the z-axis of the pipe, and transverse cross-sections of the pipe are shown here on the left and right respectively. The diameter of the pipe is given as 2 times r, where r is the pipe radius. To understand the relationship between volumetric flow rate and bulk velocity, imagine a piston pushing material through the pipe. The piston moves with a velocity equal to v sub b. In a time interval t, the piston will move a distance L, equal to v sub b times t, or equivalently, t is equal to L divided by v sub b. The volume displaced by the piston is equal to the volume of a cylinder with diameter 2r and length L, or equivalently, V is equal to pi times r squared times L. Substituting for L gives V is equal to pi times r squared times t times v sub b, which can be rearranged to give volumetric flow rate is equal to v sub b times pi times r squared, which also equals v sub b times the cross-sectional area. This relationship is used to calculate the flow rate. Process streams commonly are mixtures of different chemical species. We will differentiate the flow rate of a specific component from the total flow rate of the stream through a subscript on the flow rate. The flow rate of an arbitrary component I is referred to as m dot sub I. If a stream consists of water and methanol, the total flow rate of the stream is given by m dot. Using the letter W to represent water, the flow rate of water in the stream is given by m dot sub W. Likewise, using the letter M to represent methanol, the flow rate of methanol is given by m dot sub M. The flow rate of a component can be calculated from the total mass or volumetric flow rate. The flow rate of a component I is equal to the total mass flow rate, m dot, multiplied by the mass fraction of component I, x sub I. Mass fraction is defined as a fraction of the total mass which comes from component I. The flow rate of component I also can be calculated by multiplying the total volumetric flow rate by the concentration of component I, C sub I. Process calculations often require component flow rates in terms of moles instead of mass. The conversion requires knowledge of molecular weights, which are calculated from atomic weights. It is more accurate to speak of atomic mass and molecular mass since weight is a unit of force, but weight frequently is used. The mass of individual atoms is based on assigning a mass of 12 to carbon-12. Molecular weight is the sum of the atomic weights of all atoms contained in a molecule. Molecular weight often is represented by the letter M or letters MW. The units of molecular weight may be grams per mole, kilograms per kilomole, or pounds per pound mole. The numerical value does not depend on which units are used. A gram mole is the amount of material that has a mass in grams equal to its molecular weight. 1 gram mole contains approximately 6.02 times 10 to the power 23 molecules. This value is defined to be Avogadro's number. Note the conversion factors between moles, kilomoles, and pound moles have the same numerical values as those for grams, kilograms, and pounds. For example, the molecular weight of an oxygen molecule, O2, is equal to 2 times the atomic weight of an oxygen atom, and is equal to 2 times 16, or 32. The units may be grams per mole, kilograms per kmol, or pounds mass per pound mole. The equality of the values for molecular weight require that 1 kmol equal 1,000 moles, and 1 kmol equal 2.205 pound moles. Molecular weight will be used to calculate the number of pound moles in 1,000 grams of water. The molecular weight of water is 18 grams per mole, or 18 pounds mass per pound mole. The mass of an arbitrary component I is equal to moles of that component multiplied by the molecular weight. Thus, the moles of water can be calculated by dividing the mass by the molecular weight. Doing so and converting moles to pound moles yields 0.1225 pound moles. The calculation also can be performed by converting grams to pounds and dividing by the molecular weight with units of pounds per pound mole. The results are identical. Note that the same relationships exist between molar flow rate of component I, N dot sub I, and mass flow rate, M dot sub I. The conversion of a mass flow rate of water in units of grams per minute to a molar flow rate in units of pound moles per minute is identical to the conversion of a mass in grams to pound moles. The molar flow rate of a component can be calculated from the total molar or volumetric flow rate in a manner similar to the calculation of component mass flow rate. The molar flow rate of component I, N dot sub I, is equal to the total molar flow rate, N dot, times the mole fraction of component I, Y sub I. Alternatively, the molar flow rate of component I is equal to the total volumetric flow rate times the molar concentration of component I, C sub I. The relationships between mass and volume, total mass or volume and component mass, total moles or volume and component moles, and mass in moles are summarized in the table here. The equations for an amount and flow rate are of the same form and are given by replacing the amount by the corresponding flow. For example, the equations for mass flow rate, M dot, are given by replacing the mass M by mass flow rate, M dot. These relationships will be required to perform process calculations. The use of these equations is illustrated in this example. 4 different flow rates will be calculated. The flow rate and composition of stream 1 are provided. The total mass flow rate is 1,200 kilograms per hour, and the stream is a binary mixture of water and nitrogen. The mass fraction of water is 0.1, and the mass fraction of nitrogen is 0.9. Note that the sum of the mass fractions of all components in any stream must be equal to 1. This is true here, as 0.1 plus 0.9 equals 1. The mass flow rate of water, M dot sub W, is equal to the mass fraction of water, X sub W, times the total mass flow rate, M dot. Substituting the values and performing the calculations gives a value of 120 kilograms per hour. The mass flow rate of nitrogen, M dot sub N, is equal to the mass fraction of nitrogen, X sub N, times the total mass of flow rate, M dot. Substituting the values and performing the calculations gives a value of 1,080 kilograms per hour. The sum of the water and nitrogen mass flow rates is equal to 120 plus 1,080, which is equal to 1,200. This is the total mass flow rate. The sum of the component mass flow rates always equals the total mass flow rate. The molar flow rate of water, N dot sub W, is equal to the mass flow rate of water, M dot sub W, divided by the molecular weight of water, M sub W. Substituting the values and performing the calculations gives a value of 6.66 kmols per hour. The total molar flow rate, N dot, is equal to the sum of the water molar flow rate and nitrogen molar flow rate. The water molar flow rate has been calculated. The nitrogen molar flow rate, N dot sub N, is equal to the nitrogen mass flow rate, M dot sub N, divided by the molecular weight of nitrogen, M sub N. Substituting the values and performing the calculations gives a value of 38.5 kmols per hour. Adding this to the water molar flow rate gives a total molar flow rate of 45.2 kmols per hour.